All right, so now we're going to look at the electric field from a ring of charge. All right, now this ring, I try to draw it three-dimensionally. Hopefully it looks three-dimensionally there. You have the z-axis coming out from the center of the ring, so it's perpendicular to the face of the ring, or to the, I can say it this way, the z-axis is perpendicular to the plane of the ring. And then you have the x direction going up, y direction going kind of into the screen here. So I try to do that three-dimensional drawing, and we want to find what is the electric field at some point on the z-axis. So I'm going to put a little point here. All right, that's our point of interest, right? P. Okay, so we want to find the electric field at that point from the ring. Okay, and so we're going to do a very similar treatment to what we did before, splitting this up into segments here. There are a couple things that I want to label and describe before we actually get into setting up our integral. So one thing is that we are assuming this is a thin. It's almost like we're taking that thin rod that we had last time and bending it into a circle. So the thickness of that ring, we're not really so concerned about. I do want to highlight that it does have a radius, and that radius we're going to call capital R. Okay, let's make some of that. Okay, so I'm going to put it here. So this is a thin ring with a radius of R, and let's say it has a total charge of Q. Okay, so that means that that Q there is spread out all across a ring. Okay, so that's our situation. Maybe I could sneak in an R there, capital R. Try to do a little bit neater. There. Okay, so where do we go from there? Well, the first thing we want to do, well, we could, there's a couple ways we could do this. We're talking about a ring, right? That rod's bent into a circle. So what kind of charge density are we looking at here? We're looking at a linear charge density, surface charge density, or a volume charge density. Well, we're talking about that rod that got bent into a circle. This is still a linear charge density. This is there's no thickness with this rod here, so the charges are just are essentially in a line here, or along this circle. Okay, so we're talking about linear charge density, so lambda. And remember, our linear charge density is Q over L. Now in this case, what's L? Oh, L is a length of that circle, right? If we start here, go all the way around the circle and go back, that's our L. So what do we call that for a circle? Well, that's just circumference. All right, so Q over, and instead of L, we're going to put the circumference 2 pi R. All right, capital R there. All right, so we have lambda there, and we're quite not sure how we're going to use that yet. Okay, now what was the next part we did? So once we kind of get lambda, we get an idea of what we're looking at here, and we're trying to find our electric fields. Let's look at a couple of sections of this. So let's say we looked at, let me see if I can use my highlighter here. This section here. Okay, so we looked at that section. What is the electric field going to look like here? So the electric field coming from that section will be a little hard to draw. It's kind of going, let me see. Let me draw a little guideline for me. Whoops. Kind of going in that direction there, but you have to think about that this is a little bit outside of the plane, right? If we're looking at this part right here, this is coming out of the plane, out of the XZ plane. So kind of coming out of your screen, and so if we're talking about positive charges here, the electric field would be kind of going in this direction. Well, put it. But into the screen here. Okay, it's going behind the screen. Okay, it is a little hard to see. You kind of have to think about it three-dimensionally. Right? If this ring here is coming out as in front of your face here, coming out of your screen, then the electric field at this point is going to be going into your screen, kind of downward at an angle. Whereas if we let's pick the opposite side of that. The opposite side of that would be this side down here. Okay, so that side down there, which is behind the screen, behind your computer screen. And let me get a little guideline here. That's going to create an electric field coming out of the screen, going this way. Whoops. Oh. There you go. Okay, so if I keep picking points here, that's going to draw it. If I keep picking different points, so I keep highlighting different little segments of charge. So like this segment here, this segment, and I keep picking different segments here. All right, I'm not going to keep those there. But if I keep picking segments and drawing the electric fields, what do I get? Well, as I draw these electric fields and I start to draw more and more electric fields here, I could draw a couple more. They start to add up, and they kind of make, it's really weird. You get to think about this three-dimensionally here. As I start to add them up, what you will see is that they kind of make a cone here. Let's see if I could draw that. Okay, they kind of make this cone where some electric fields are in the positive x-axis, some electric fields are in the positive y-axis, some electric field has a negative y-axis. So you have all kinds of components here, right? If I split up the components, I have, whoops, that's not components. If I split it up into components, I have x components, right, going like this and like this. Okay, but not only that, I also have I have a big z component. I'll do that black here. I'm going this way because they're all adding up going in the z direction. And I also have y components. Right, y components go in and out of the page. So, oh, that's too thick. Okay. So I hope you're able to see that three-dimensionally there. That I have my x components. I have if I split these. Let's see, where's my? Right. If I split these vectors into components, I have some components going in the positive x, some components going in the negative x. Right, here's my x-axis here. So those are going to cancel. I have some components going in the positive y, some in the negative y. So those are going to cancel. The only one that doesn't cancel are the z components here, right? So we just took into account the symmetry, and you should be able to see that this is symmetric in the xy plane, right? So you have this quadrant is symmetric to this quadrant is symmetric to this quadrant. So whatever electric field this guy produces is canceled out by this guy on the other side. Whatever electric field this quadrant makes is going to be canceled out by this quadrant, okay? So due to symmetry, the x and y components cancel. Okay, so now all we have are the z components. That's all we're interested in. We're just interested in the z components here. Let's see, I don't know where to put this. Let's put it right there. Okay, so I'm going to focus in on just one of these charges. And since we know the x and y components cancel out, I'm going to erase a lot of this here. I'm going to pick a component, a charge that makes it easy for me to draw here. I'm going to focus in on a segment of charge. Okay, we're going to focus on a segment of charge up here. Okay, that segment. I don't know if I could do this. Okay. Now, in that segment of wire, just like we did when we talked about the rod, do this in red here. Okay, we have how much charge do we have in each segment, right? If you look back at how we did the rod, we said the rod has a charge dq, okay, and it has a length dl. Okay, that's what we do for pretty much every single problem that we're looking at. There's always going to be a dq and a dl, right? And how we define that dq and the dl, it's going to be different as we go through this. Okay, so so now let's draw a little wire here, a little guide wire. Not wire, but just a line to help me draw it. So this little piece of charge on top of the loop here is going to produce an electric field going in this direction. Okay, so that's going to be my DE. Okay, and we want to find the Z component, right? That's what we're after, because the X and Y components cancel out. We just want to find that Z component here. Okay, so DEZ. So how can I get DEZ? Okay, well, this is theta. Right? If I call that theta, I could find DEZ by just doing DE cosine theta. Okay, now we got to plug in for both of these, right? We got to plug in for DE, and we got to plug in for cosine theta. Cosine theta is be pretty easy. We just kind of do the same trick we did last time with our triangles. A little different there with what this triangle actually means. But let's talk about DE first. What is DE? So DE, we start off kind of the same way we did with the rod, which is use Coulomb's law. Now, don't get confused with lowercase r and uppercase r. Lowercase r here is talking about the distance from DQ to your point of interest. So in this case, DQ is up here. Our point of interest is here. So we're talking about this distance right here. That's what lowercase r means, lowercase r. Uppercase r is talking about the radius of this ring, all right? So they're talking about two different distances. Don't get those confused there. And it comes up a lot, uppercase r and lowercase r. So lowercase r is actually talking about the distance from the charge to the point of interest. Okay, so what substitutions can we make here? Well, let's make a substitution for dq, right? We've done that before. We said that if we look at lambda is q over L, and we could say the same thing, that we're just talking about ratio of charge to length. dq over dl. Okay, so kind of we do the same trick we did last time, where if we set lambda equals to dq over dl, we could solve for dq and plug in lambda dl. All right, so let me go a little slower in case you didn't see that. So lambda, let's see, equals dq over dl, and all we're doing is rearranging that to be dq equals lambda dl. Yeah, that's what we're doing there. Okay, and then r squared. Well, what's r squared? Well, r squared is this distance here. Let me highlight that there. We'll go right here. Okay, is that distance. Now, we got to figure out what that distance actually means. So let's make a triangle here. If I make a triangle, You know, maybe like I have this line here, and then I have another line here. Okay, what values do we have that for those sides of the triangle? So for the sides of the triangle here, we're looking at this side of the triangle. This green side here, let's just call that z, right? It's along the z-axis going to some point on the z-axis. So I'm just going to call that distance z. Okay, z. What about this distance here, the red? What's that from the center to the top? You know, to the top of this arc here. Well, that would just be the radius, right? Which I have right here. So this is a radius. This little arrow is a radius. This red line going from the center to the edge is your radius. Okay, it looks different because of the perspective that I was trying to get there, but so that's radius there. Okay, so what would r then be if we're talking about this distance right here, the hypotenuse of my triangle here? Well, r in that case is just, let me put that here. Square root of z squared plus r squared. Z squared plus r squared. Okay, now because it's being squared here, the square root will go away, right? This square root and this squared make it go away. Okay, so here's my dE. Actually, we can even talk about something a little bit, let's talk about it now. I was gonna talk about this DL later, but let's talk about this DL now. So DL is this length right here. So let me draw a circle and just ask you guys, how would you say this, what would be the length of, let me see here. What would you call that length there? All right, here. Well, we could just call it DL, but let's relate it to some of the values we're given. Let's relate it to radius. If I draw these lines, make it a little bit. I go to the center. Let's see if I could do this. Hey, come on. There you go. Okay, so this is radius r, and this is some small theta, right? So small angle. So if I'm saying that this is DL up here, DL, and this is d theta. How are all these quantities related? DL, R, and d theta. Well, if you remember arc length equals S equals R theta. So the length of the arc is just R times the angle. Well, in this case, if we're talking about DL, that's my arc length. This DL is just related to the d theta by the same equation. So I will put it as DL equals R d theta. Okay, so now we're getting even more specific, and that's what you want to do when you're doing these derivations here for these different geometries. You want to make sure everything is defined. So leaving it as DL is not good, because now, like, what's DL? I have R, I have Z. How is this related to those? And this is where this comes in, right? The DL equals R d theta. So that DL is R d theta. And we have Z squared plus R squared. Okay, now remember, this is all DE. There you go. Okay, so this is all DE. It's not DEZ, right? So we know that all the components cancel out. The X and Y components cancel out, except for the Z component. So now that I have DE right here, let's see if we can get that cosine theta. Well, this theta that we defined is the same theta here, is it? Same theta. So if we're talking about cosine theta, Well, cosine is adjacent over hypotenuse. So we could use this triangle that we have here, this triangle, to figure out what adjacent over hypotenuse is. Okay, so let me plug in what we know. So DEZ, here's our DE, K lambda R d theta. Oh, actually, you know what? That's okay. So K lambda R d theta over C squared plus R squared. And cosine theta, what's cosine theta? Now, you know, there's a couple of ways I could think about this. Let me do it this way. Cosine theta, adjacent over hypotenuse, Z over square root of Z squared plus R squared. Okay, so let's simplify that. K lambda R, oopsie. Z d theta over, and then we have that Z squared plus R squared to the 3/2. Okay, so that's our DEZ. Okay, now that we simplified DEZ, what do we do next? We got DEZ here. What do we do next? How do we get the total electric field? Well, that's where our integration comes in. Put that in a different color now. So to get EZ now, our total electric field from the ring, we'll just do integral DEZ. And when I do that, let's see, let me plug in. So K lambda R Z all over C squared plus R squared to the 3/2 d theta. Okay, so I want to show you something here. What are constants here? As I go out to around this circle here, go around this circle, what are my constants? Well, K is a constant, so actually let me go down here. Hopefully I have enough space. So EZ, let's take out my constants. K is a constant. Lambda, right? If we assume uniform charge density, I didn't say any otherwise. So we're going to take lambda to be constant. What else do we got? We have R, the radius. Well, the radius of the ring, well, that's a constant. What about Z? Does Z change as you go to different parts of the circle? Right now, if you imagine this triangle is going to be rotating, right? Rotates around that circle, but that Z is staying the same. Okay, the Z axis is staying the same here. So if the Z axis, this value for Z, not just Z axis, but the value for Z, if that's staying the same, that means they're essentially constants. So I could factor out Z outside of an integral, Z, and I can factor out that Z squared plus 1/2 or plus R squared 3/2. And all that's left is integral d theta. Okay. So what is this theta referring to? This theta, you know, I know now I'm thinking about it, probably should use different angles. I'll talk about that in a second. This d theta here is referring to this d theta, right? This part of that circle, which is this circle. I just drew the circle from a different perspective. So this d theta, we're going to go around the whole circle, right? So what is for d theta? What's the value if you go around the whole circle? Well, you're going from 0 to 2 pi. Whoops. Okay, so let me make a quick note. I made a misstep here. I mean, algebraically, everything's fine, but just something kind of confusing. I would call this theta here, and then I call this d theta, right? These actually are two different angles. I perhaps should have called this like alpha or or beta, or some other angle other than theta. So because it is referring to a different angle than this d theta is. So that was my bad. I should have used a different angle. So let me just make that correction right now, because they're talking about physically different angles, right? They're different locations. This one's between the y-axis. I'll call it phi. Okay. All right, so that I'll recall this cosine phi. So yeah, I wasn't being careful enough. Yeah, two different angles there. Okay, so that's just a side note. Didn't really change anything because once we saw cosine phi, it's still adjacent over hypotenuse, right? We still get the same ratio. Also, if you thought that this is d theta and you were thinking, well, couldn't we just integrate cosine theta? That's why that would be incorrect, because this is actually a different angle. This phi and this theta are not the same angle. So you wouldn't keep this cosine and then do cosine theta d theta, because again, this is a different angle. It's not referring to the same physical angle as we see here. Okay, so sorry about that. I hope that didn't confuse you too much. Everything else is still correct here. Okay, so a lot of simplifying at this point. So here's all the I'm just going to do all the simplifying in one shot. K, what's K? Well, I'm going to put K in terms of the 1/4 pi epsilon 0. That's K. All right. What's lambda? Well, lambda we have over here. All right. Lambda equals Q over 2 pi R. So I'm going to put that. I'm going to have to erase this. Let me just move it. Okay. Okay. So lambda Q over 2 pi R, capital R. Then we have R. Then we have Z. Down here we have Z squared plus R squared, 3/2. And then the integral d theta gives us 2 pi. So like I said, a lot of canceling out here, rearranging things. Let's see. Don't think I'm going to be able to fit this, but we'll try. All right, so let's see what cancels. So this 2 pi here is going to cancel with this 2 pi here. This radius, capital R, cancels with this capital R. And I think that's it, right? So I guess I didn't have to substitute for K. Nothing happened to this 1/4 pi epsilon 0. I think later on it will. But because I'm eventually going to use this to talk about a disk of charge. So I guess I could just keep this as K. It doesn't really get affected too much. So let me revert it back to K. I thought I was going to cancel out that pi or something, but I didn't. So K, Q, Z over Z squared plus R squared to the 3/2. All right, so that is the equation for a ring of charge. Okay, so we're going to use this equation for a ring of charge to derive the equation of a disk, and then eventually derive the equation for an infinite plate. So we're going to use it in a little bit, but just to highlight a couple things here before wrap this video up. The approach that we did here was very similar to the approach we did as a rod. If you walk through the video, try to watch this video again. May not, you don't have to watch the whole thing, but watch the video again and try to see what were the steps that I took. What was the general approach? So I drew out a picture, right? I had a little picture here, drew a point, And then I started defining, well, this would have been defined in the problem. Radius R, charge Q. I define what kind of density we're going to use, right? Lambda in this case, linear density. And then once I did that, then I looked at symmetry. Right, that symmetry saved us a lot of time. We didn't have to worry about DEX or DEY because we know they canceled out. It was 0. Okay, and then once we saw symmetry, then it gave us some direction. If X and Y components canceled out, then we know we just have to look at the Z component. Okay, and then that's what led us through all this algebra here, and then a little bit of calculus there with the deep data, but hopefully you saw that all these things were constants, right? As you go around the circle, nothing in this equation here changes. K is staying the same, lambda, R, Z, all these things are staying the same. So I could factor it out, and it's just really simple integral, at the end of the day. All right, so look over that one, try to get the method down, not so much the exact step-by-step, but that you could see the thought process and what my logic was as we work through it. All right, so next time we're gonna use this equation and get the disk. What is the electric field from a solid disk? So we'll do that next time.